is something that in fact is used widely in biology and in statistics. It's used in metabolomics, it's used in microbiome studies and genomics, transcriptomics, proteomics. It's frequently used in phylogenetic analysis, evolution, protein classification, protein sequence families, over and over. Clustering is a process by which objects that are logically similar in certain characteristics are grouped together. Clustering is something that we might do naturally when we're sorting laundry. It's something that we probably did as kids when we sorted rocks. It's different than classification. Um, Classification is something that a geologist does with rocks. Clustering is something that a kid does with pebbles. In classification, the objects are assigned to predefined classes. In clustering, the classes have yet to be defined. So when you cluster things, it helps sometimes to define classes. So if you recall the height and weight graph that we saw, there was some, two clusters. It was only when we classified them as male and female that it was possible to really clarify what the clusters were and why they existed. So to do clustering, you have to have some kind of measure of similarity or dissimilarity between objects. You also need a threshold to decide whether something should be part of a cluster or not. You also have to have some way of measuring the distance between two clusters. And then to start clustering, you always have to start with something, a cluster seed, some kind of object to start with. There are different similarity measures. People can use things like the Pearson correlation coefficient that we've talked about before. Or we can use Euclidean distances, or the mean absolute difference, or just simply the difference. Among the different clustering approaches, there are two main ones, k-means clustering and then hierarchical clustering. K-means is sort of to group things and objects into m clusters without, generally with overlap. Hierarchical clustering is essentially a nested way of clustering things. There are self-organizing feature maps. I'm not going to talk about those in detail. K-means clustering follows a fairly simple algorithm. If you've got a bunch of objects, say colored balls, you could just randomly choose one object and say, make that the center of the first cluster. Then grab a random object and determine how similar it is to the centroid. If the similarity is greater than a certain threshold, add that object to that cluster and then recalculate the centroid. And then you repeat the process. So in pictures, it's probably a little easier to understand, but we can have these 5 different colored balls. We can use the color spectrum to decide whether things are going to be in the centroid or not. So if we randomly choose one cyan colored ball, we use our threshold rule. We'll identify a little darker cyan color, and we'll say that those two fall within the rule. We'll cluster them and join them, and then we'll recalculate what the centroid or average color should be, and we'll determine which ones should be added next. As I say, that can be repeated. Now, in hierarchical clustering, we try and form a nested set of objects, and we try and connect all of them together in some way through some line of similarity. So in hierarchical clustering, we typically have to perform a comparison or pairwise comparison against every object in advance. And then once we've found the ones that are most similar, then we match them up. And then we bring the next most similar ones and bring those together, the next most similar ones, and the next most similar ones, until all of them have been clustered together into this one giant cluster. So this is illustrated here. So we start off with 5 balls again. We do pairwise comparisons against all of them. identify the two that are closest, and the next one that's next closest, and then the next one and the next one, until we finally get all 5 connected. The result is something that we call a dendrogram that sort of identifies the relationship between the closest, the next closest, and the next closest pairs until we get this family lineage, if you want, that creates almost the appearance of a family tree. So hierarchical clustering is a little different than k-means clustering. K-means, we can have clusters that are well separated, whereas hierarchical clustering, it tries to put them all into some giant heat map or family tree. Now, we're going to switch again to multivariate statistics, because we spent most of our time focusing on univariate statistics, correlation, and clustering. Now, with multivariate statistics, we're now looking at multiple variables, measuring multiple components in a set of subjects or a population. And what we're going to see is that many of the same things that we saw in univariate statistics are repeated in multivariate statistics, but in a slightly different way. So as I said, multivariate statistics involves multiple variables. It means not just measuring height alone, as we've done for most of our examples here, but it might mean measuring weight or hair color or eye color. Or in metabolomics, it might mean measuring not just creatinine levels, but measuring 20 amino acids and 30 organic acids and 50 biogenic amines. Multivariate statistics inherently is more complicated. It's a multidimensional analysis. But you can simplify a lot of multivariate statistics by doing something called dimension reduction. And we'll talk about this a little later. The other thing to remember in the metabolomics experiments that are often done is that we measure multiple subjects to serve as biological replicates. If everything was uniform and if variations were stark and significant, we might arguably only need to measure a single subject as a case and a single subject as a control. But because there's a fair bit of variability in humans or animals or plants, we have what we call our biological replicates. And so this is why we typically measure 30, 40, or 50 cases, along with 30, 40, 50 controls. We can also develop technical replicates to ensure that our instruments are measuring exactly as expected or as required. So whether it's metabolomics, genomics, proteomics, transcriptomics, we'll often have both biological and technical replicates. In metabolomics experiments, we will measure many metabolites on the biological replicates. And so all metabolomics data is inherently multivariate data, and therefore metabolomics requires the use of multivariate statistics. The trick in multivariate statistics, and this was determined way back in the 1920s or 30s, was to try and convert it to be similar to univariate statistics. And this is this form called dimension reduction. When you can reduce things to sort of a more simple form, instead of having 10 or 100 dimensions, but something like 2 or 3 dimensions, then you can start using standard univariate concepts like p-values and t-tests and q-tests and ANOVA tests. And then it starts making sense again.